Yes, yes.
Yeah. So, good morning, everyone. So, welcome to the 5th edition of this ST Forum. So, as you all know, this is a very friendly platform. So, we all are, some of us are MSc students, some are graduates, and some are postdocs. So, the idea means the purpose of is to be friendly during the discussions, during the lectures, ask friendly questions, and okay, so there are some rules to ask the questions. Okay, so let me brief you about the rules, the Zoom rules. I mean, how to use it. Okay, so mute your microphones at all the times. So if you want, you can also turn on your video during the lectures. Also, you can turn on your video. Okay, and the second one is when you are asking the question, you at first you raise your hand. You can find the option raise hand below of the participants there, so you can raise hand here, and then the moderator will tell you to unmute yourself, and then you can ask your question. So in during the asking of question, you can turn on your video also if you want. If you feel free, then you can turn on your video also. So if you cannot unmute during means if you cannot unmute when asking the question, then what you can do, you can post your question in the Slack channel. So just use the Slack channels. Means suppose today we have Entanglement entropy by Jyotirmoy. So use the doubly Jyotirmoy channel in the Slack, and you post your question there. Then the moderator will track the question of that, and he or she will ask the question to the speaker. Okay, so these are some rules. Please mute yourself during the all lectures. And okay, let's welcome Jyotirmoy. He is doing his PhD from IISc, and he will give his lecture on entanglement entropy. Okay. Subham, can you?
Jyotirmoy, can you start sharing your screen, maybe?
Yeah, sure. Is it visible?
Yeah. Yes.
Okay. Should I start now?
Yes, yes, please.
Okay. Thanks. And this is going to be about entanglement entropy in quantum field theory and conformal field theories. So I'll be discussing only free theories, and framework is going to be based on the field theory framework. And we will be interested to evaluate entanglement entropy of ground state of quantum field theory and conformal field theory. So I have sketched out the plan of my lectures. The first lecture is going to be the introduction or setting up the definition of entanglement entropy. And towards the end, we will approach towards evaluating entanglement entropy of the ground state of quantum theories, in particular pre-quantum theories. Lecture 2 onwards, we will set up definition, path integral definition, and I'll work out conformal fields, I mean, the conformal scalar in arbitrary dimension and Maxwell field in 4 dimensions. That's the rough plan of my lectures. So, okay. Let me start. So, entanglement entropy is an useful quantity to characterize a quantum system because it essentially captures the degrees of freedom of a system. So what do I mean by that is the degrees of freedom I mean is the number of scalars, number of fermions, or number of gauge bosons present in the system. And it turns out that for conformal field theory, the universal contribution of entanglement entropy is proportional to the central charge of the field, which means, and also we know that central charge is a function of number of scalars and fermions and gauge bosons in pre-case. So therefore, entanglement entropy basically tells you about the degrees of freedom of a quantum system near about a critical point. Although it is useful and interesting quantity, but it's hard to compute, and even for the free theories, and in particular if the theory admits a gauge symmetry, and very few exact results are known. Uh, these are some statements, which we will justify and clarify as we go along. Okay, so let me start by defining entanglement. Now consider we have a 1D spin-chain system, like we have a spin degrees of freedom, and you imagine cutting it at 2 points and subdivide the space into A and B subsystems. Essentially, what it means is that you factorize the Hilbert space. Sorry, you factorize the Hilbert space in H A times HB. The factorization of the Hilbert space is done. Now you trace out or integrate out the degrees of freedom present in one of the Hilbert space. So you trace out or say integrate out degrees of freedom of subsystem A or B, and finally you construct a density matrix or the reduced density matrix by tracing out the degrees of freedom in one of the Hilbert spaces. So rho A is defined by tracing out the degrees of freedom in the Hilbert space. So similarly, you can define rho B by tracing out the Hilbert space A. So what we have done is the first step is to factorization of the Hilbert space. Then you integrate out or trace out the degrees of freedom in one of the Hilbert space, and you construct a reduced density matrix. Now you can compute the von Neumann entropy of the corresponding reduced density matrix. So the von Neumann entropy, is defined as trace of rho A log rho A, and this is defined as the entanglement entropy of the subsystem A. So this is nothing but the von Neumann entropy. Okay. Now what I have said in words. So now consider a state which is denoted in psi, is written as AB A B. Here I have already factorized the state in two Hilbert spaces A and B. Now you can readily compute the density matrix psi, which will be AB A prime B prime C A B and its complex conjugate A prime B prime A B A prime B prime. Now you compute the reduced density matrix. Reduced density matrix is computed by tracing out the degrees of freedom present in the Hilbert space E. So rho A will be sum. You put B equals to B prime and sum it over B C star A prime B. Here the Hilbert space B is traced over. So in the basis of AB A prime B prime, this is the reduced expression of the reduced density. Now entanglement entropy is.
Jyotirmoy, do you have the ket and bra also?
Yeah, I mean in the basis of A and B, and AB and I'm writing it in the basis. These are elements.
Okay.
So therefore, the entanglement is the basis. So therefore, the entanglement entropy is von Neumann entropy.
Sorry, do you mean A prime? The
Yeah, because B is summed over.
yes, okay.
is the entanglement entropy of the subsystem A. Okay. Now, let's define another quantity which is known as Rene entropy. Which is defined 1 by 1 minus q log of base of rho a raised to the power q. But q is Rene parameter. This is the definition of the Rene entropy. And people usually do is first compute the Rene entropy and
there is a question. Shubham, please ask your question.
Can you go up a bit above this, where you are summing over, where you are defining the reduced density? What did you say about the? So why are there four? So just go to the reduced density definition of reduced density. I mean, it should be a comma a prime, just right? No b.
Yeah, correct. Because b I have written because it's summed over. I mean, just to clarify.
Okay.
This is, of course, the indices are a prime, correct? And b, that's why I said b equals to b prime. The three indices are a and a prime. It's a matrix. Correct. Okay. So this is the definition of the Rene entropy. Yeah, where q is denoted as a Rene parameter. Now, people usually do first compute the Rene entropy, this quantity, and then take limit q goes to 1 to define entanglement entropy. So entanglement entropy is limit q goes to 1 by 1 minus q trace of rho a to the power q. So let me prove this statement. This identity, the little task. So what you do first is Taylor expand rho a to the power q about q equals to 1. So SQ is 1 by 1 minus q, because we are going to take limit 1 goes to q goes to 1. So that's how, I mean, that's why I Taylor expand around q equals to 1. Log. Okay, so the first term rho a, then rho a log rho a at q equals 1 times q minus 1 and order of q minus 1 squared and other Taylor expand terms. Now the normalization condition we know is that trace of rho a is identity. That's the definition of the normalization condition of the density matrix. So you write log of trace of rho a is 1 plus q minus 1 trace of rho a log rho a and order of q minus 1 square times and 1 onwards. Now you further expand log of 1 plus x, use log of 1 plus x plus other terms. So q minus 1 trace of rho plus 1 square. Now you can see that if I take the limit, only the first term is going to contribute. So all the other terms will drop out because in the limit of the q equals to 1. This is going to be minus, because q minus 1 and 1 minus q, trace of rho a log rho a. And this is the 191 entropy precisely. And entanglement entropy. So the steps are like, so first you, in generally, people evaluate Rene entropy and then take limit q goes to 1 to evaluate entanglement entropy. Okay. So any questions, comments, anything?
Shubham has a question. Shubham.
Yeah, I mean, why would you? I mean, is it easier to compute this Rene entropy?
Yeah,
That's
yeah,
why you
and
do it.
because in the case of field theory, one sets up the rho a to the power q, the definition of the rho a to the power q in a path integral framework quite easily. So people follow that path.
I see. I mean, okay. I mean, so it's computational simplicity.
Correct, correct. But sometimes one can use the definition of entanglement entropy directly to evaluate entanglement entropy. Because in that case, sometimes it happens that entanglement entropy is just mapping of thermodynamic entropy. So that is easier sometimes.
I see.
Because in a thermal ensemble, it turns out to be the thermodynamic entropy.
Okay.
Chirag has a question. Chirag.
Yeah, hi. So what is this Rene entropy is telling me? Like, what is it physically? Like, by looking at the expression, I can get like it's like one parameter generalization of this
Correct.
entanglement entropy.
Correct.
But in physical sense, is it some long range correlation or something like that?
I'm not sure, but it shouldn't be a long range because it depends on the UV. I mean, Rene entropy or the entanglement entropy should depend. I mean, depends on the UV cutoff of the theory, and it doesn't depend on the IR. So it shouldn't be the long distance thing.
Okay, so in that case, just the like
It's just
generalization
one,
of
generalization of that. Correct.
But since this entanglement entropies and these things are measures of correlations, right? Whether you talk about some quantum field theory,
I mean,
finite
yeah,
dimension.
measures of correlation. I'm not sure because in generally correlation has a classical analog because you have a I mean Green's function, classical analog.
Mhm.
But in generally entanglement entropy doesn't have a classical analog, so it's purely a quantum phenomenon.
Okay.
I shouldn't.
But
I mean, I don't want to call it a correlation or something. It's just defined in this way.
but then classically you have the Shannon entropy, right?
Yeah, there is, of course. But this rho A is
Yeah.
reduced density matrix of a quantum system. Let's define in this way.
Okay.
Buddhaditya has a question.
Yeah, hi. Can you explain in maybe in short or something, why is it harder to take log of the density matrix as compared to the power source of the density matrix?
Because you have to compute first the density matrix in a field theory framework first. So if in field theory framework, first you have to subdivide a space-time region, and there is a short distance entanglement. You have to, I mean, integrate out the rest of the spaces, and then you have to take, I mean, you have to define the state, then rho A, log rho A things. But it turns out to be that if you take rho A to the power q, you end up getting a partition function on some q-fold power, which will come in the next lecture. But
Okay.
yeah, but sometimes that one is easier.
So basically there is no geometric way to do the log.
Yeah, I mean there is holographic, of course. I mean holographic way of doing it.
Holographic is different, but like you can
Yeah, of course.
for calculating powers you can put it on a manifold. This you can't do for log.
On a manifold, what do you mean?
Like when you calculate higher powers of trace of rho, I mean higher powers of rho, you put it on an n manifold
Yeah,
or something.
you create n such sheets, and
On
those
the n
are
sheets.
the path integral setup. I haven't even started. I'll do it in the next lecture.
Okay, sure. Thank you.
Okay. So my handwriting is pretty
Yeah,
bad.
can I ask a quick question? Sorry.
Yeah, okay.
Yeah, is there a physical interpretation for the Q, parameter Q? So far, there is no, I mean, it's just an arbitrary variable.
It's arbitrary integer so far. It's arbitrary integer, and one generally analytically continues it to 1 to get the entanglement entropy. I don't. I have no idea if there is any physical interpretation.
Okay.
It's
So
just a parameter.
I see. So for this is only, I mean, the only reason we are even worrying about this is to reach the one Neumann entropy at some point.
Correct.
Someone has a question.
Yeah, just I want to. So you just, 2 minutes ago you said that this Rene entropy or entanglement entropy doesn't have a classical analog, and there was a question about how you can relate it to correlation functions, for example. But I would like to say that Rene entropies can be written as 2-point functions or twist fields in CFT. So
yeah.
How does this fit in with this quantumness that you just explained? That it's a completely quantum phenomenon.
But those correlators are quantum correlators, isn't it?
In twist fields, you can have, I mean, once you have replicated manifold, you can have twist fields. That's all I get.
Yeah, I mean, do you
there is nothing quantum in that, right? I mean, twist fields you can have just when you have replicated manifolds, you can have twist fields even in classical picture, I would imagine, if I'm not wrong.
So is there any Green's function for the twist field? Twist field, I know
there is a 2-point function for the twist fields because they have well-defined dimensions, and you can write a 2-point function. Let's take the conformal field theory where we know how to construct the twist fields, and then you can write the dimensions, right? And there is, I was wondering where exactly this quantum is coming, but I agree with you that this entanglement entropy is a quantum phenomenon. But what's bothering me is that if I can write it as a 2-point function of twist fields, where exactly this argument is falling down.
Yeah, but I mean the twist field I know is just imposing a boundary condition on the fields. Like when you just use the replica parameters, you just put the field on first sheet.
Exactly, but there's no quantum in this, right? It's you can do it classically. You have some bunch of classical free fields, and you can put these boundary conditions and define those twist fields such that you just go around this branch cut or this point where the branching happens, and you go up to the second sheet, right?
Okay.
Where exactly is the quantumness here? That's bothering me.
Yeah, because I thought in that way. I mean, I'm not sure. I agree with you that, yeah, of course one can write it in terms of the correlators of the twist operators.
Huh.
Yeah. So in that sense, yeah, you can say.
Okay. Okay.
Yeah.
I have a small question.
Subramania, can you ask the question?
Can you hear me?
Yeah, I can.
Yeah, sorry.
Ravita, can you wait till Subramania?
So, are there any inequivalent entanglement entropy definitions, or rather measures of entanglement entropy, where it is not equivalent to the so-called von Neumann measure that you are writing? Because Rene entropy ultimately you can reduce it to von Neumann measure.
Correct.
But are there any inequivalent definitions of the similar entanglement entropy?
Oh, I don't know, to be honest.
Okay. Thank you.
Shubhu, if you have a question.
Hi. So I just wanted to comment on Anish's question. So the significance of Q is that basically there are infinite number of local unitary invariants. So that is what this is telling us. So when Q goes to 1, that limit is a special quantity, von Neumann entropy. But in principle, if you want to classify entanglement classes, all Rene entropies of all Qs are relevant. Like you can use all of them to quantify entanglement. So is that
if in that from that perspective, what exactly is Q?
Oh, it just says there are those many numbers. For each Q, there is a particular Rene entropy, right? And you can compare and you can classify that that if two systems have Rene entropy at order 1 to be something, then what is the Rene entropy at order 2 and so on. So if that is different, then they belong to, I think, different entanglement classes.
I see. So even from that perspective, Q is just doing something, but we don't know what it is doing. I mean, what Q equal to 1 and
it
Q
is defining different.
I mean, I understand
maybe it's not a physical interpretation, but it is just an index. Yeah.
So I think we should ask more questions about this in Slack. Let Jyotirmoy continue.
Yeah. Okay. So let me just point out few properties or general properties which will be useful. So properties. So first thing I'm going to show is for pure state, it turns out that entanglement entropy of a subsystem A is same as entanglement entropy of subsystem B. So to prove that, you start with a definition of trace of rho A to the power Q and trace of rho B to the power Q. So I'll do it for Q equals to 2, and you can convince yourself for arbitrary Q. So first you do trace of rho a squared. So rho A is defined as CAB, C star A prime B, because B is summed over. Similarly, C another A prime B prime, A prime B, yeah, A prime, yeah, A prime B, and sorry, A prime B prime, and sister B prime A. So this is first row A, and the next one is the second row A. And finally, you can see this A index is same as this index because there is a big trace sitting outside. Now you rearrange like this. You bring the last one here, sister B prime A, C A prime B prime, sister A prime B. Now it seems that A is summed over. A is summed over. And the whole B is tracing over the B is sitting outside. So you can write it down as, so since it's sum over A, which means rho B. Is it okay? Because first here A is summed over, A is summed over, A is summed over, and then B is summed over because of the total trace sitting outside. So therefore, trace of rho A squared is same as trace of rho B squared. Now you can prepare Q such rho A, trace of rho A to the power Q, construct trace of rho A to the power Q, and rearrange it to show it same as trace of rho B to the power Q. And you know the definition of Rene entropy is SQ is 1 by 1 minus Q and trace of log of trace of rho A to the power Q. And since trace of rho A to the power Q is same as trace of rho B to the power Q, the Rene entropy of subsystem A turns out to be the same as Rene entropy of the subsystem B. Therefore, entanglement entropy of subsystem A turns out to be same as entanglement entropy of subsystem B.
Rita has a question.
Yeah.
Just one thing I just want to for myself. So this trace rho A square equals to, you have written this as a product of CC errors. So this is the property of purity, right? You said
Correct.
when A and B both are pure states. Correct. So I'm just trying to see.
Yeah.
Yeah. So this is writing this is like equivalent to saying.
Correct. Because otherwise you would have sum over I, Pi, and so on. But Pi would be different for each state. So you can't just bring it up and just make it like that.
Oh, okay. Yeah. Okay. Thank you.
Okay. So it has a nice physical significance. So if you are, is there any question?
Yeah, hi. So in this case, when you have a pure state, or for all Q, this trace rho A to the power Q is equal to trace rho B to the power Q. But is this like an if and only if condition? Can you like check it for all Qs, and if that holds, then we can claim that it's in a pure.
I think it's if and only if, because otherwise you can't bring it like this, because you'll have a sum over Pi's for each density matrix.
Okay. So is it possible that these two are equal for some Qs and not for all Qs in a mixed state?
Some Q and not all Q. I mean, Q is just multiplication of rho A. You multiply rho A Q times.
Yes.
And some Q and all Q, I don't get.
So I mean, I'll rephrase it a little bit. So if you're in a mixed state, will this condition be violated for all values of Q necessarily?
I guess it is, because I mean, because you can't write for Q equals 1, because rho A is of course different from rho B.
Okay.
And yeah, and you can by the method of induction, I guess you can prove it. You start with Q and then you show it for the Q plus 1.
Yes. Thank you.
Could you say again? Why it works only for pure state?
Sorry.
I thought you said that entanglement entropy matches only for pure state. Could you say that again? So,
entanglement entropy matches with the sorry, I didn't get it.
Am I audible clearly or?
No, I can't hear you properly.
Oh, sorry. Give me a second. Go on, I'll ask you later. Thank you. Okay.
So
I think he's asking you to explain the issue about pure state and mixed state. Like this relation is not valid for mixed state. You said something about sum over pi. Maybe you can explain it a little bit.
Yeah, because in a pure state you can only write, the density matrix in the following way, right? Pure state. Otherwise, you will have for the row mixed state, you will have a sum over I, pi, and pi is different for each psi I, for the each density matrix. So you can't just bring down the elements here because pi will play a role. Okay.
Okay.
Tanay has a question.
Yeah, hi, Jyotirmoy. I just want to know one more thing. So you said that for limit q tends to 1, the Rene entropy is equals to the von Neumann entropy. What about the other extreme limit? Let's say when q is very large.
I don't know any quantities known. I don't know. One can check. So for example, q goes to infinity. It's divergent because rho a to the power q is divergent because it's multiplication of that, and 1 by q it goes as 1 over q, right?
Yes.
So I think it will diverge. I'm not sure. If anyone can say anything, comment on anything.
That is something that you check, right? Whether your
of course.
So if rho a to the power q is divergent, then you know that rho is like greater than 1 and you have some problem. But if it is less than 1 and convergent, then you know it's like a way below.
Correct. Okay. So we have seen that SA is same as SB. So it has a nice geometric way of interpreting it. Geometric interpretation.
So Anish has a question in the chat. He's asking, when people refer to entanglement entropy, is it always Rene or is it von Neumann?
Yeah, people refer it von Neumann, but for the computational perspective, people start with Rene and then go back. One can just do the entanglement. Okay. So in generally, in quantum field theory, people associate a Hilbert space with a particular space-time region. So for example, let's consider a sphere, and two subsystems are inside the sphere and outside the sphere. Now for a pure state, you say, we call it A or B. Now for a pure state, you say that SA is same as SB, which means that if I want to associate entanglement with a geometric quantity, this has to be common in between A and B, right? And the only common geometric quantity which is common in between is the area of the entangling surface. This is the entangling surface. Therefore, entanglement entropy is proportional. In the leading order, it's the area of the entangling surface. That's why people call entanglement entropy is not extensive quantity, rather intensive quantity, and it follows the area law. That's why people say it. And also entropy is a number, scalar number. So therefore, there has to be, area goes as L squared or L to the power d minus 2 in arbitrary dimension. So therefore, there has to be some scale which scales the area such that entropy becomes a number. And you have two scale at it. One is UV cutoff of the theory and the IISc. And you know that entanglement is a short distance phenomena, and it should not depend on the large scale present in the system. So therefore, it depends on the UV cutoff of the theory in precise, which is epsilon, and raised to the power some number, so that it balances out the dimension of the entanglement entropy. So yeah, sorry. So is it okay? Someone wants to comment on anything? No.
Yeah, seems okay.
Okay. but I'll prove it. I mean, this is just a naive argument. This is just a naive argument to show that entanglement goes as the area, it follows the area law. But I'll prove it precisely towards the end of the lecture
So
if I can.
isn't this a comment only about the divergence? Only about the divergence?
Yeah, it is a divergent quantity, and of course a UV divergent quantity. Is that what you asked?
No, I'm just saying, is this area dependence only comment about the divergence, right? But like, I mean, even if you change, insert some operator far away from the partition surface, you will see a change in the entanglement.
Yeah, of course, because I mean, if you you can see that, I mean, if you change the UV cutoff of the theory, the area term would change, and it's part of the divergence. What you were saying, yeah, correct. Because if you rescale epsilon to 5 epsilon or something, there will be some coefficient sitting outside, and it will change. But this is the leading order of the divergence. To be honest, this is the leading order divergence.
Anish has something to say.
Yeah, based on that question. So suppose you have a UV complete theory, then what is the scale?
I mean, I guess it's always starts with the area term. It's always area divided by for arbitrary d greater than 2. But in d equals to 2, it starts with a logarithm. I'll come back to it. The general UV properties of the entanglement, I'll come to it.
Okay. No, what I was confused was that if you have a cutoff, I mean, and if you have a UV complete theory, I can take the cutoff all the way to infinity, right? And in that sense, I mean, is the entropy well defined? I mean,
I don't know any UV complete theory. Entanglement of any UV complete theory is known, well known. I don't know, to be honest.
I see. Okay.
Okay. So let me give the complete the UV behavior of the entanglement entropy. So in general, for d greater than 2, it starts with the area term. And it follows the power series expansion. And you get a term which is log in even dimension. And in d equals to 2, it starts with log. And this is d greater than 2. It starts with the log. And in odd dimension, this is in even dimension. In odd dimension, it also starts with the area log, because this is true for arbitrary dimension, and follows the power series expansion. And finally, you get a constant gamma. And I write this term and this term specifically because this is the universal. This is called the universal contribution of the entanglement. Because you see, if you just change the cutoff of the theory, the coefficient in front of it doesn't change. And this is the area term. Similarly, in odd dimension, this is the universal term, because if you change the cutoff of the theory, it doesn't change. So when in the follow-up lectures, when I'll be saying the entanglement entropy, I'll be saying about the universal contribution of the entanglement entropy. And for today, I'll prove the area law. But later on, when I'll say the entanglement entropy, it is the universal contribution. Okay.
Shivam has a question.
I can see some, yeah.
Yeah. So, so my question is, you seem to divide a region always in such a way that the region A is a bounded, so that you can define an area, right?
Correct.
But what if you divide the region in some other way, like by straight line or something, so that the region A is not bounded?
Correct. That will change the area term. That's a good question. So, for example, you have a region, let's say in 2D, and you have a circle. So that will change the area term, the first term, because so suppose I mean in 3D you can think of a sphere, the area of the sphere and is different from the box. You can also divide the space-time in by using a cubical box. So the area term would change, but the universal contribution doesn't change. So when when I say the entanglement entropy, it will be precisely the universal contribution. The area term would change. That's a good point.
Okay, thanks.
Akhil has a question.
Hi, so how do I see that the series reduces by powers of 2?
That I'll prove it. I mean, I'll prove it. I mean, it precisely comes from the regularized volume of the areas. I mean, I'll prove it. But you can think of I mean, naively you can think of in a way. So suppose you are given a quantum system. Now you evaluate quantum entanglement numerically first. You don't know, you are given a mass parameter and so on. You evaluate numerically and you try to plot S with first area term, and then you can try plotting with some other AI R by epsilon, let's say D minus 3. You try to plot it and you will see significantly that A1 or A, let's say 3 or 4, this coefficient is significantly smaller than A0. Just naive understanding. But there is a precise statement behind it. I mean, if you want to just convince yourself.
Yeah, I'm convinced. I just was looking for a hint to guess it. Yeah.
Yeah, I'll prove it later. I mean, second or third lectures. Yeah. Any other question?
Adrita asked a question in chat. What is R in the universal term of the second equation?
Oh, yeah. So here you can see universal term means that doesn't depend on the UV cut of the theory. For example, in odd dimension, you see it doesn't depend on the epsilon explicitly. But for the even dimension, you can see if you just change the UV scale, I mean, the UV cut of epsilon to 5 epsilon, it will just log of 5 epsilon is log 5 plus log epsilon. So you can still bring it down here. So, and the C coefficient doesn't change in front of it. So that's what it means. If you change the UV cut of the theory, the term which doesn't change is known as the universal term. Is it okay?
Yeah. Anisha.
Yeah, so I had some internet difficulties. So I don't know if this was answered, but there was somebody who asked the question, what if the entangling surface has infinite area, if I understood that question correctly. And I don't think I understood the answer. So suppose you have, let's say, a three-dimensional space, and you, let's say, look at x equal to 0 hyperplane separating the two regions. Then the entangling surface has infinite area. So in that case, what exactly is the entanglement entropy infinite? I mean, like
no. I mean, entropy. The area term would be infinite in that case, but the universal term would be.
I see. Okay, so okay, I see.
But when I say the entanglement entropy, it is the universal term because it doesn't depend on the. I mean, when you say the complete x-axis or the complete xy plane, of course it is infinite.
Right.
Then
okay,
you have to also think that how do you subdivide a region? If you consider the entire system to be the entire plane, what is the other subsystem?
Right. No. I was just thinking like I mean but I mean I naively expect the entanglement to be to infinite in the example that I just said. In 3D, if I just have, let's say, the x equal to 0 hyperplane, that separates, like, x less than 0 and then x greater than 0 region. But of course, you have infinite area over which it can entangle, and therefore the entropy can be infinite. So I just wanted to know whether the intuition is correct.
Yeah.
Okay.
Yeah. Correct. Is it okay, or are there other questions?
Yeah, there is one. It's okay.
Is it okay? I mean.
Yeah, you can continue.
Okay. Yeah. So, so what we have seen is that entanglement entropy has a leading order behavior, which is area term, and it has a universal term as well. So, but I haven't proved the area property precisely, but I had given some argument to follow whether it follows the area law. Let me start with a system which is two-coupled harmonic oscillator. Two-coupled harmonic oscillator, which I'll generalize it to n-coupled harmonic oscillator because I want to finally go to quantum physics. And let's understand first two-coupled harmonic oscillator and evaluate the entanglement entropy of the system. So the Hamiltonian of the system we know is plus. So this is the natural spring constant. K0 is the natural spring constant. And this is the coupling. You can have in mind in free field theory, you have the Hamiltonian, which is integral. I mean Hamiltonian density. This is so you have phi square plus phi square plus some massive. If it's massive, you have n square phi square. So the grad phi is precisely the coupling between phi and phi at x plus delta x. So this will mimic that term. I can see some questions. Is there any other?
No.
Okay. So correct. So we have the Hamiltonian given given the equation. Now we want to evaluate the entanglement of the ground state of the system. So the ground state of the system can be written by going into the normal mode coordinate system, because normal mode decouples the harmonic oscillator, the coupled harmonic oscillator. So you define the normal mode coordinate x1, x minus x2. There could be I'm not sure. Yeah, there is. Yeah. Okay. And in the normal mode coordinate, you can write the Hamiltonian square where omega plus and omega minus are the function of the natural spring constant and function of the coupling spring constant. So the normal mode coordinates x plus and x minus, basically decouples the harmonic the coupled harmonic oscillator, so that you can write down the ground state of the system as a product of the two decoupled harmonic oscillators. That's the idea, to write down the ground state of wave function. So therefore, you can write psi ground state of x plus x minus as a product of the ground state of the oscillator, first oscillator, now in the normal mode, and the oscillator in the system. So you know phi x plus and phi x minus is the ground state wave function of harmonic oscillator, which is like Gaussian. So this is 1 square root phi plus omega minus exponential minus square x minus. Okay, now you go back to the original coordinate x plus x minus to x1 coordinate. You just replace x plus x minus by this x1 x2. So we have got the wave function, the ground state wave function of the two coupled harmonic oscillator. Now you have to compute the density matrix and the reduced density matrix. The density matrix is quite easy, just psi star. So sorry. Density matrix is just psi x1, x2, psi star, x1, x2, and x prime. Therefore, the reduced density matrix will be computed by tracing out or integrating out any one of the harmonic oscillators. It's either one or the two. So here I am integrating out the first oscillator. dx1 and rho of rho. This is rho, and let me just simply write psi of x1 x2 psi of x1 x2 prime. So you put x1 equals to x1 prime and just integrate over x1. And you know the expression of the psi is purely Gaussian in x1 x2. So this integral is quite easy to perform, and you get something gamma minus beta. I'm not doing the integral, you can check it. Exponential of 2 x2 squared x2 prime squared and beta x2 prime, where gamma and beta are the function of the frequencies of the normal mode oscillators. 4 minus plus times omega minus divided by omega plus plus omega minus, and the beta is without alternatives. So we have got the density matrix, a reduced density matrix, which is function of x to x2 prime, because we have integrated out the first oscillator. Now we need to know the spectrum of it, because ultimately what we want to evaluate is the entanglement entropy, which is minus trace of rho a log rho, or in the diagonalized version where lambda I log lambda I, but lambda is the eigenvalue of the reduced density matrix. Now we first solve the eigenvalue equation of the reduced density matrix rho a. Rho a has this function alpha. So the eigenvalue equation for the rho a would be rho a, which is a function of x and x prime. It's a two. It's in a matrix, you know, you have a 2 index, and some eigenfunction fn x prime equals to some lambda n fn x eigenfunction. Now you have to integrate over tx prime, because this is the dummy index. This is the eigenvalue equation, and you know rho a has a Gaussian in nature. Rho a has a Gaussian in nature. So if you want to get back fn, if you multiply fn and you want to get back fn has to be either Gaussian or a polynomial multiplied with a Gaussian. Because if you integrate out in that case, you get a Gaussian back. Because you know, if you have like e to the power minus ax squared, e to the power minus bx squared, and you integrate, you end up getting another Gaussian. So I can see some question. Is there any question, or I can just go on?
You can go on. It's a discussion.
Okay, great. So it turns out that, I mean, this is the case of the solution that, I mean, I should mention that all these calculations is based on the paper by Strednicki. Name of the paper is Area and Entropy. Entropy in 93. I'll post that paper in the Slack group. Okay, and it turns out that the eigenfunction fn x is a Gaussian, precisely e to the minus alpha x squared multiplied with a Hermite polynomial, where alpha is omega plus omega minus square. Now what you can do is check this statement. Check, if plug it back the function fn, and you do perform this integral, which is quite easy, and because it's a Gaussian, and check what the lambda gives. And it turns out, if you choose this function fn to be Hermite polynomial multiplied with the Gaussian, then lambda n turns out to be beta by gamma plus alpha to the power n 1 minus beta by gamma plus alpha, where beta alpha is defined as a function of omega plus omega minus, and beta and gamma I have defined it earlier, which is also a function of the gamma beta is a function of omega plus and omega minus. So you've got the eigenvalue. So let's call beta by gamma plus alpha is zeta. Let's call it zeta to the power n by 1 minus zeta. So you've got the eigenvalue lambda n. Now what we have to do is to compute entanglement entropy is sum over eigenvalues, all the eigenvalues, lambda I log lambda. Now you note that this zeta, which is beta over gamma plus alpha, zeta is beta by gamma plus alpha is less than 1. Why? Because beta, you can see there's a relative sign, and omega plus omega minus are all positive thing. So beta over gamma is a less than 1. So therefore zeta is less than 1. And you can do this sum easily by geometric, the geometric sum. So entanglement entropy could be minus lambda. Lambda is what? Zeta to the power n 1 minus zeta log of zeta to the power n 1 minus zeta. Which you can write it minus zeta to the power n 1 minus zeta, and you just separate it out here. Log n log zeta plus n log zeta plus zeta to the power n log of 1 minus zeta. Yeah, log of AB, log A plus log B. Log B, so there is no zeta. Correct. Now this is a geometric sum, which you would require is x to the power n. In first case, this is like when you want to compute this term, this is just x to the power n sum, where x is less than 1, 0 to infinity, which is 1 by 1 minus x, and you need to know n x to the power n minus 1, sorry, n x to the power n because of the first term. And this you get by differentiating the first ddx of this. This summation is well known. It's just simple geometric sum. And finally, what you get entanglement entropy is finally what you get is log of 1 minus zeta minus zeta by zeta. Okay, this is the expression of the entanglement entropy of the two harmonic oscillator, where zeta is of course a function of gamma beta, which is also a function of the normal mode frequencies. So finally we end up getting entanglement entropy, which is a function of the normal mode frequencies. So I mean this expression we will require to derive the incoupled harmonic oscillator as well as the quantum field theory in case of the quantum field theory. Yeah. So any questions so far? Comment.
Yes, Ritabh.
Yeah, I just wanted to ask. So in this case, you've taken like the system one as to be the coordinate x1, and you have integrated x1 to get that way, right? But means like from the earlier picture, can we see any like distinguishing surface or which like distinguishes the system A and B? Means I understand here you have only calculated the universal part, right? So two dimensions.
Yeah, this is universal part. I mean, this is a discrete system. In the universal term is actually in the quantum field theory, where epsilon is the UV cutoff. Here, I don't have any UV cutoff of this. This is two oscillators, a discrete system. And you just compute the entanglement by just computing the reduced density matrix of the eigenvalues of the DGs, which is a finite. Reduced density matrix is a finite quantity.
Yeah. So it's like in case of a discrete system, you don't really need to divide it up into a system and subsystem like A and B.
I mean, you can divide a subsystem in two subsystems. Here my two subsystem is oscillator 1 and oscillator 2.
Yeah. Okay.
Any other questions? Okay, let me go on. So let's understand the source of the entanglement. So you can imagine if we have a free, not coupled oscillators, you won't get any entanglement. And you can imagine, of course, it should come from the coupling constant K1, which couples the two oscillators. So consider a weak coupling limit where K1 by K0 is much less than 1, where K1 is a coupling constant and K0 is a natural spring constant. Now see how omega plus and omega minus here. Omega plus is square root K0, it goes as square root K0. Omega minus is square root K plus K0 plus 2K1. It also goes as K0 because K0 is much greater than K1. So therefore, the gamma, which is 1 4 omega plus omega minus plus omega minus, and omega plus omega minus both goes as square. Both goes as square root K0. Therefore, it also goes as square root K0. Now for beta, which is a relative sign, and one has to be careful in expanding in Taylor series. Since there's a plus sign, you don't have to bother. I mean the order. Now since there's a plus, there's a minus sign or the relative sign, you have to expand it quite, carefully. And it turns out that you expand it like K1 by K0, and you collect the leading order term. And it turns out that the leading order term is precisely K1 square divided by K0. Therefore, zeta, which is beta by gamma plus alpha, but alpha is significantly small, so I am taking beta over gamma. So beta over gamma is K1 squared divided by K0 to the power 3 by 2 and square root K0, which is K0 squared. So zeta goes as K1 squared over K0 squared, and we have taken the weak coupling limit, which is K1 by K0 is much smaller than 1. Therefore, zeta is the eigenvalue. I mean, not zeta is the eigenvalue. Lambda is the eigenvalue, which is a function of zeta. And we have evaluated the entanglement entropy as a function of zeta, which was in the previous. Yeah, this is the expression. Now you substitute this step. Because zeta goes as K1 by K0 squared, you can just expand, and zeta is significantly smaller than 1. You can expand log of 1 minus zeta a and keep the leading order zeta. And what you get is entanglement entropy goes as K1 over K0 squared log of K1 over K0. And it also goes to 0 because K1 is much less than K0. So you can see that if coupling constant, the strength of the coupling constant is much lower than the natural spring constant, you don't get any entanglement. And the entanglement is purely coming from the coupling constant K1. So the source of the entanglement entropy is the coupling between degrees of freedom. Okay. Now, is there any questions?
So here, if K1, I mean for finite K1 by K0, this is negative, is it?
Finite K1 by K0. Yeah. Because log K1 by K0 is, and it doesn't matter. I mean, you asked whether entanglement entropy is negative or not, but you will see sometimes it is negative. It depends whether you put the UV cutoff. I mean, for example, so log R by epsilon is a universal contribution in field theory. Now you can call this as a universal contribution, or you can call epsilon by R. So it doesn't matter. I mean, what matters is the magnitude in principle. Yeah. Any other questions? Okay. Now let me go on to derive the n-coupled oscillators, which will mimic the QFT case. And I'll do it quickly because the method I have developed for the two-coupled oscillators, I'll just need the answers. N-coupled oscillators. So here the Hamiltonian would be S square plus half
Anish has a question.
Yes.
Yeah. So I just want to understand one thing. So in the previous example, right, the entanglement is for a given time, right? I mean, at a particular time
It's a
slice.
constant time slice t. You can think it at t equals to 0 at a constant time
Zero
slice.
at some constant, and presumably the n-coupled harmonic oscillator is also
Yes.
at some constant time slice. But
Right.
in the geometric way that you wrote down the differentiation between A and B, I mean there could be entanglement across time also.
Correct.
So is there a meaning? So I'm not very familiar with entanglement. So is there a way that I can understand what it means?
I'm answering. Yeah. So when one says the entanglement entropy, it means that a constant time slice, because that's why you get the area term d minus 2. D minus 2 means you have two constraints. One is you have one hypersurface, because which you subdivide the two systems, and the time, you fix the time. So that's why it's a co-dimension 2 object.
I see.
So yeah, so when we say the entanglement entropy, it means at constant time slice. But one can evaluate the time dependent phenomena, and in that case, time dependent. Since I'm doing the ground state, you can excite the ground state by using. I mean, in CFT one does it by using primary operators. You place the primary operators in two different times, and you create an excited state, and you evaluate the time dependent phenomena of entanglement of the excited states.
Okay.
So
okay.
those have a nice interpretation.
I see. Okay.
Yes. So these are all at constant time slice. What I'll be doing in the lecture so far, in future as well, all of them will be in constant time slice.
Okay.
So therefore, the Hamiltonian is this, and the ground state just the product of the Gaussian. Sorry, here Kij is a symmetric real matrix, and omega squared is K. I define omega squared as K. Pyramid of 4 divided by 5 n to the power 4. You can see it's a n coupled oscillator, so n to the power n by 2 exponential of x. This is a ground state with the Gaussian. Therefore, density matrix you construct by taking Psi and Psi star. Now I write omega in a different way. So k square is the omega, but k is the real symmetry matrix. I mean the potential matrix in precise. So I write k omega, which is k squared matrix, which is the n by n matrix, right? Because k is n by n matrix, and I write the first. I subdivide, because ultimately I'll have to subdivide the system, right, to get the diffusion matrix. So if first one I subdivide n by n, and the second diagonal part C, which is n minus n times n minus n. So this is basically the n by n matrix, small n by small n matrix, and that this is capital N minus small n times capital N minus small n. So that, I mean, the total dimension is capital N. And here you have a B matrix, which is n minus n times n, and this is the transpose, and because K is symmetrical, n times n. Now you know that this is when you write the x, you write x is the position of the all the oscillators. X1 dot dot dot. So I write it in this way: x a and x r, where a runs from 1 to small n, and I runs from n plus 1 to capital. Is it clear? So this is basically subdividing. Now what I'll do is I'll trace out this n minus n oscillators, or integrate out n minus n oscillators. So therefore, the density matrix, the reduced density matrix, which will be I running from n plus 1 to capital N, because I'm integrating out that n minus n oscillators, and rho of the density matrix, which is a function of x a x I Is it okay? Now rho, you know, rho is given. All you have to write x in this way, xa xi. Omega, you plug in this a b transpose c, and you integrate over the last n minus n oscillators. This last n minus n oscillators. And finally, what you get, rho a is there is a square root of determinant will be sitting outside, because when you integrate out the Gaussian, you get a determinant. So what you get, I'm not writing it, the determinant minus half xa. So xa will be there because you are integrating xi's, which are the n minus n1, the oscillator. Gamma xp, I'll define everything. System will be xp and etc. Beta xp. So you see that since we have integrated of the I oscillators, so-called I oscillators, which are n plus 1 to n, you end up having a reduced density matrix, which is n by n, small n by small n, because x a runs small n, I mean 1 to small n. And you look at the expression which I did for the which I derived for the two harmonic oscillators, rho a, and it has a similar expression. You see, there is a determinant sitting outside. You get gamma over 2 x2 x2 prime and beta x2 x2 prime. Gamma by 2 x2 x2 prime squared plus beta x2. So x and gamma x prime and the beta. But gamma and beta are no more just simple constant. They are matrix because xa is n by n column vector. Sorry, n column vector with n. So now what you do is now diagonalize this gamma, because ultimately you need to evaluate the spectrum. So gamma, you diagonalize it by this way. That diagonalizes the xa prime. Therefore, reduced density matrix becomes minus a half of y prime y squared. Sorry, square prime squared plus y lambda and lambda is a function of the gamma and beta matrix. The gamma, sorry, define the gamma becomes c minus half of b transpose a inverse b, where b, c, a all comes from the omega. Okay. And finally, you remember there was a lambda coupling in the two harmonic oscillator, and in that case, we got lambda to be zeta to the power 1, lambda zeta to the power n 1 minus zeta. Here we will get eigenvalues of the lambda matrix, capital lambda, which will be again zeta to the power n, zeta I to the power n, of course, because there are small n by small, actually small n number of eigenvalues, zeta I. And finally, do entanglement entropy of any one. First, you do one eigenvalue corresponding to one eigenvalue. This would be the definition of what we derived for two harmonic oscillator, 1 minus zeta by 1 minus zeta.
Sorry, just one thing. So shouldn't this be ya prime lambda ab yb? Or in that expression above, shouldn't it be ya prime lambda ab yb?
Because xa prime x2, correct. It should be ya prime, correct. Thanks. Yeah. So you have got zeta I for the corresponding the s of zeta I for the corresponding ith eigenvalue. Therefore, entanglement entropy would be sum over all zeta I, because you have a n number of eigenvalues. minus. Okay, so this is the entanglement of the incoupled harmonic oscillator. Any questions? Okay, then I can go on deriving it for the scalar field, and the idea would be based on the canonical quantization. And what I want to do is basically write down the Hamiltonian of the scalar field in terms of the n-coupled oscillator, and I finally put the field on a lattice, field theory on a lattice, and I'll treat it as n-coupled harmonic oscillator. Okay.
Jyotirmoy, there is 15 minutes left.
Oh,
Do you think that's enough?
I don't think I'll be able to complete it. But
how much time would you need?
25 minutes should be good. Let me try. I mean,
Okay.
Let me try.
Okay. Yeah, you can take 5 minutes.
Yeah. So we have a. I'll do it for the scalar field in 4 dimensions and the masslessness. So first, I'll have to define subsystems, right? So you consider a space at a constant time slice. You have a three spatial dimensional area. I mean, 3 spatial dimensions, and you subdivide the space-time by sphere. Inside the sphere is subsystem A, and outside of the sphere is subsystem B. And what I need to write is the Hamiltonian, because I want to mimic the n-coupled harmonic oscillator. So the Lagrangian density would be r square d omega phi dot square. It's a function of dr grad phi in the radial direction, because Lagrangian like del mu phi, it has a grad term. Grad phi because we have a 3 directions. So let me just at a constant time space, let's say t equals to 0. We have a 3 direction r, and I denote it I. I is the direction on S2 because it's at a fixed r, it's r, and this is a 2-dimensional sphere. So the I coordinates transfer the 2 angular direction on sphere. So therefore, I'll have a grad term in the S2 as well. Correct? This is okay. Now, what I want to do is when you write down the Hamiltonian or the modes of the Hamiltonian, you just use the mode expansion. For example, in 3D free case, the mode expansion you write phi as some k, phi k to the power k. So free wave expansion. Here I'll use the symmetry of the problem because I have a sphere. So therefore, I'll use spherical harmonics as my mode expansion. So mode expansion. So phi er ln phi ln. This is the mode. So what we used to write in phi k is similar to phi ln, and spherical harmonics yln, which is a function of theta and phi with the angular 2 direction on S2. Now you come, because you need to evaluate phi dot grad phi and grad phi on the S2. So you do phi dot tr ln. It's the only time dependence comes from this mode to the mode phi ln tr. Time doesn't heat on theta phi, and you want it, and grad phi in the radial direction. Grad phi in the radial direction will hit on the phi ln, because y ln is a function of theta and phi. And similarly, grad phi on the 2 angular direction will hit now on the spherical harmonics, because it depends on I. Y ln theta phi. Good. Now we know the orthogonality condition of yln. Yln star ln is prime n. So now I'll write the Lagrangian in terms of modes. So this is the Lagrangian, and I'll replace those modes back here, and I will perform the omega integral and use this orthogonality condition. So Lagrangian becomes r square here. Then d omega 6 outside. Ln L prime n prime phi ln dr phi, so phi dot, because first one is phi dot n prime n prime dr. Then we have k dot phi ln phi L prime n prime. Of course, there is phi ln phi L prime n prime phi ln L prime. Now phi ln will sit outside, and the grad will hit on del I this is the grad along the S2 direction. Now what you do is now use the orthogonality condition. The integral d omega yln yl prime n prime, which you substitute delta ll prime, l as l prime and n as n prime. But you remember also that yln is like yln is PL, legend of polynomial, e to the power I m phi. Now when you do the d omega integral, there is a phi integral here, because d omega is like angular 2 angular dimension also. You will have e to the power I m phi and I m prime phi, and this will make m prime as minus m. Correct? Therefore, you just substitute it. This orthogonality condition is substituted. Orthogonality condition you use this to write the Lagrangian in terms of the mode r square dr sum over lm, because that orthogonality condition will remove one of the sum. You get phi dot lm phi dot l minus m del r phi lm del r phi l minus m. Now here the last term you have a del I ylm and integration over d omega outside. So you can perform on one integration by parts and move del I over here, one integration by parts, and use del I the Laplacian on ylm as minus L into L plus 1 for r square ylm. This is the eigenvalue equation of spherical harmonics, and you substitute that. What you get finally is L into L plus 1 by r square pi L n by L minus. So this is the Lagrangian in terms of the mode. We have expanded. How much time do I have?
5 minutes left. Maybe we can give some time for questions.
Yeah.
Also, I think he started a bit late, so like 5 minutes late. So we can, I think, put the cutoff at 12:40 maybe. Yeah.
Okay, so let me just carry it out.
Yeah.
So great. So we have got the Lagrangian in terms of the modes. We have expanded, and now we want to write down the Hamiltonian. Hamiltonian is a function of phi and phi. So first you do the canonical conjugate momentum phi ln, which is ln del phi dot ln. Here you can see it's r square phi dot phi ln. Therefore, you write Hamiltonian phi ln dot minus the Lagrange, and what you get is half outside integral r square dr all is 6, because we are not touching it. Ln phi ln minus phi minus over r to the 4 plus L minus n, and the L part, L into L plus 1 r square phi m square. So this is the Hamiltonian. Now you can see it still doesn't look like the n-coupled harmonic oscillator, because n-coupled harmonic oscillator has a p squared, of course, and half of kij xij xi. And if we know the equal time computation relation is satisfied by the modes phi lm by I delta. These are at r prime, r minus r prime, equal time computation relation delta L prime delta m prime divided by root g. Root g is needed because I'll see, because you know the property of the delta function. It's delta x minus x is unity, but in covariant space you replace it by root g d cubed x, and you have to have by root g downstairs so that the equation matches. So the equal time commutation relation for the pi and phi, and there is a root g downstairs because of that. It is. But if you have a flat space, there is also a flat space, but in Cartesian coordinate, root g is 1. So you have delta x minus x. Now you rescale phi and phi because you want to make it look like p squared and x squared. You scale phi and phi. I define phi tilde as r phi and phi tilde as r phi. So therefore, you can see there is a minus because xp has a computation relation I. Therefore, you see phi tilde and phi tilde will have a delta r minus r. Because 1 by r will come and that r square will be cancelled. So finally, in terms of the phi tilde and phi tilde, Hamiltonian becomes integral dr lm phi tilde lm tilde l minus m plus r square r plus L into L plus 1 L. Now note that this looks like exactly like the n-coupled harmonic oscillator. This mimics the pi square term, and this is xi kij xj. But the kij matrix has to be defined carefully because xij will involve the derivative on phi and also phi. And you remember from the two harmonic oscillator, you have x1 minus x2 coupling, like x1 minus x2 square. And it precisely comes here because of that del r, because it couples phi at point r and phi at r plus delta r. So now you put it on lattice. At this point, you put it on a lattice with a lattice spacing A, and A inverse is your UV cutoff. Therefore, Hamiltonian in lattice 1 by 2a, sum of I equals to 1 to n, pi l m I for each lattice point I, pi I squared. R square, I'll write it as, you can write it as I squared because that's the lattice point. I'll write it as I plus half squared. I'll explain why. And grad phi, you write it as pi ln I by I minus pi ln at I plus 1 because it couples I point with I plus 1. I plus 1 square and L into L plus 1 I square pi square. So I have chosen I plus half. I'll tell you the reason. Because you have a lattice, you have a capital N number of points. Let's say this is the ith point, and this is the I plus 1. So when I subdivide the region, I'll take the boundary in between. This is the ith point lattice, and I'll integrate out I plus 1 onwards, and this will not be integrated out. And I put the boundary in between two, I and I plus 1. That's why the I replace R by I plus half. Okay. So this is the lattice form of the Hamiltonian I wanted to write. How much time? 12:30. Maybe I should stop here because it will take some time again.
Yeah.
So later, I mean, the next lecture, I'll compute the entanglement entropy using the n-coupled harmonic oscillator, because I have the n-coupled oscillators now, and let's see what it is. Okay.
Akhil has a question.
Hi. So now you would also do something to change the boundary condition of the fields to the left of the surface. Or?
Yeah. I'll impose a boundary condition. The first boundary condition would be like phi lm at capital N plus 1 and phi lm at capital N plus 1 is 0, because that's your lattice limit. Like n number of oscillators you have, N plus 1 is 0. That is the boundary condition. But the boundary condition in between, like I and I plus 1, will not be changed, because we are like having a boundary in between I and I plus 1. I'll not change the boundary condition at the ith point.
So I'm confused, as in, if you're thinking about the Hilbert space of the things towards the left, you would want the wave functions to be to go to 0 or something, just like a particle in a box, right?
Yeah.
Wouldn't you want?
Yeah, correct. I mean, this boundary is imaginary boundary. Like it's not strict boundary, so that like you put phi I plus 1 onwards is 0. It's not true, because you can also integrate out the first ith oscillators. Then this is not 0. The other one is not 0. This is some imaginary thinking of subdividing a Hilbert space. You're just imagining I'm dividing it first I, first n, and then n plus 1 to capital N. It doesn't mean you stop the modes after n plus 1 to capital N modes. We're not stopping the modes.
Okay, thank you.
So we have some time for questions. Please ask. Raise your hand. Jyoti has a question.
Hello.
Yes.
Is it possible to compute in momentum space, because even there also we have a mode expansion?
This is the momentum space, means this is mode. Can you please clarify which momentum? You want to write in k and k minus k, something like that?
Yes, if we go to, like, if we do a Fourier space expansion, even then we have an inharmonic oscillator.
Correct. Then the lattice will be in momentum space lattice. Correct?
Yes.
Then you have to integrate out the n oscillators in the momentum space, and you would have to come back in the original lattice space. It's possible, but cumbersome, I guess.
Okay. Thank you.
Yeah, hi Jyotirmoy. Thanks for the talk. It was excellent. So I have a very basic question to ask. So let's say you have a system for which you are computing Rayleigh entropy, and then in the leading order, or Q goes to 1, the von Neumann entropy is the same, and then in first order, the entropy is different. There's some different number for the two systems. Then can you comment on something about microstates?
Microstates.
Yeah.
You want to write the von Neumann entropy as a number of microstates, is it?
I know. What I'm asking is, let's say Rayleigh entropy, you are calculating Rayleigh entropy for two systems, A and B. And then in the Q goes to 1 limit, both of them have same entropy. It turns out to be having the same numbers in Q goes to 1. But the next order, it's a different number for any entropy. Okay.
Next order.
Then can you say anything about the microstates? Because
what do you mean by next order? Next order is what?
In Q minus 1, you have expanded in a Q minus 1, Q around 1, right, in Taylor series.
Okay, correct.
So first order is the von Neumann entropy that I have some ideas about what is its relation with the number of microstates and all, right? So what I'm asking in the next order, if that is different for two systems, then what can you say?
So what I want to mean is that suppose you have a row, you prepare A and B, you prepare row A to the power Q and row B to the power Q. And what it turns out that the spectrum matches entirely. So row A and B are of different size. Let's say in terms of discrete way, row A, let's say 3 by 3 matrix, and row B is, let's say, 20 by 20 matrix. What happens is that, I mean, if A 3x3 matrix has 3 eigenvalues. Let's say 1, 2, and 3, lambda 1, lambda 2, and lambda 3. Then those 3 eigenvalues will also be present in the B subsystem, and rest will be 0. Like in the B subsystem, if you have a 20 by 20 matrix and 20 eigenvalues, 3 of them, three eigenvalues will be same with the A matrix, but 17 will be 0. So when you do rho A to the power Q and rho B to the power Q, if it matches with the first order, I guess it should match it in all order.
Okay, if it matches with the first order, it matches with all order.
It should. I'm not sure. I haven't.
Yeah, that's what I was asking. Okay.
Yeah.
Okay. Thank you. Thanks again for the talk. Yeah.
Yeah. Hi, Jyotirmoy. I'm still a bit confused about this I plus half business. So you have replaced R as I plus half in the second term, but not in the third term.
Not in the third term. Oh, sorry.
Or not anywhere else where I occurs. It's only there.
No. When I replace R, I mean not here the R square. You can replace it I by I plus half. I mean I plus half here or I plus half. Ultimately, you'll see it doesn't matter. Finally, it doesn't depend on the I, and it finally depends on the I, because the number of oscillators you count.
Okay, I see.
You'll see that you can write it any way possible. I mean, you can replace I plus half squared by I squared or I minus 1 squared.
Okay, thank you.
Ritabrata, please ask.
Yeah, to begin with, in the last part of the talk, thank you for the nice talk. So in the last part of the talk where you have used the spherical harmonics to do the mode expansion, so there you assume like it's the system on a sphere, so you had spherical symmetry. So when you put it on a lattice, that spherical symmetry is broken, or did you implement the boundary condition to actually?
No, I mean this is a one-dimensional lattice, because you see the lattice is on the radial direction. At each radial point, you put a sphere.
Okay, I see.
So the lattice is one-dimensional, radial direction.
Okay, thank you.
Any other questions? Okay, thanks.
I